Okay, let me repeat. Today we're going to do section 3, subtraction of whole numbers. Subtraction simply means reduction in size. It's the inverse, the opposite of addition. The definition of subtraction is for any whole numbers a and b, where a is bigger than b, a minus b is the unique whole number c, such that b plus c equals a. This is what it says. A minus b equals c. That's true as long as b plus c equals a. For example, if a is 3, b is 1, it satisfies the condition a is bigger than b. A minus b, 3 minus 1 is 2. But if we flip them around, b minus a, 1 minus 3 gives you -2. -2 is not in the whole numbers. That's how come a has to be bigger than b. And that's where we say subtraction is not closed under the whole numbers. What do we mean by not closed? No. A system is closed if after any algebraic operation, the result or the answer is a unique number in the system used. By system, here we're talking about whole numbers. We could just be talking about integers, or we could talk about counting numbers. So that's the system. Once you define where your numbers are, then we can see is the algebraic operation add, subtract, multiply, divide, is that closed? Meaning, if I do any operation, let's say a plus b. If a is a whole number and b is a whole number, it means it's only positive numbers. Like 0 plus 0, is 0 a number in the whole number system? Yeah, so that means it's closed. But subtraction is not, because if we commute the numbers, it's no longer in the system. So that's why I'm saying it's not closed. All right, so now we're going to look at the models of subtraction. By models, we mean theorems, theories, procedures. The first model is called the takeaway model. And we're going to do a lot of these examples. Our examples are going to use blocks, manipulatives, and numbers. So take away. Let's say we had 43 minus 11. So what does that mean? Using blocks, how would we represent 43?
I mean, by putting 43 blocks, but then stack. We can do like a stack of 10.
Yeah, we have the bars. Those are each 10. We have 4 of those.
You can have like four small individual, I mean, three.
And we have 3 individual blocks, right? That constitutes 43. 11 is we have 1 bar and 1 box. So the takeaway model says this. I could take away, I'm taking away 1 long bar and 1 small box. So what I'm left with is 3 long bars and 2 small ones, which is equal to 32. So 43 minus 11 is 32. Which is exactly how we do it algebraically. 3 minus 1 is 2, 4 minus 1 is 3. What if we had this? 31 minus 15. We have 3 long bars. And 1 box. I want to take away 1 long bar and 5 boxes. Can we do that?
I think some of the 5 boxes that I want the long bars.
Right, because we don't have 5 boxes here to take. We have to take one of these. Remember, these are worth 10. So we have those 10 plus 1, so we have 11. I took away 1 bar and I put it in the ones. All right, so now I get rid of those 4 and that 1 and get rid of this one. So it leaves me with 1, 2, 3, 4, 5, 6. So this equals what? 10 plus 6 is 16. And we do it. So we know that 31 minus 15. I can't do that, so I got to borrow 10 from there, which gives me 11. 11 minus 5 is 6. 2 minus 1 is 6 is 1, so 16. That's stuff we've been doing, but this is how we show it. So that's the first model, the takeaway model. The second model is the number line model. So let's do something small for right now. So we start with a number line. And we start with whole numbers only. Knowing that going to the right is positive and going to the left is negative. So we start with the first number. It's a positive 8. So we start at 0. We go over 8 spaces. That's 8. And then from that, where it stops, since I'm going backwards, and I go 3 spaces, 1, 2, 3. So 1, 2, 3. Which says my answer is 5. How do we check that? Mm-mm. Remember the rule.
Oh, yeah, if B, if A equals B, then B, if A minus B equals C, then B plus C.
Right. So it's 8 minus 3 equals 5. This is A, B, C. Then B plus C has to equal A. So it's 3 plus 5 has to equal 8. And it does. That's how you check your subtraction. The third method is called the missing addend model. In A minus B, A is called the minuend. B is called the subtrahend. Subtrahend. Now, what this one says, the addend is this number here is called the addend. For example, one way of teaching, a good way of teaching subtraction is if I gave you this equation. Well, remember, you're teaching it elementary school kids. I know what we know is that just subtract 3 from 8, which is what we got to do. What we got to do is we can only use these numbers here. So what's missing here is, as you said, it's 8 minus 3. So take whatever the answer is, subtract the part you have. So whatever that is, that's our addend. 8 minus 3 is 5.
You know, we can say, yeah, we would just have to move the three to the other side.
Remember, that's using the properties of mathematics. The identity property. This or the inverse property. But again, elementary school kids won't know that. That doesn't get taught until 5th, 6th, 7th grade. Now, why is this important? Because if I had 8 minus 3, then since I know that 3 plus some number equals 8, 3 plus 5 equals 8, then 8 minus 3 has to equal 5, as you said. And the fourth model is the comparison model. Where you compare two sets of numbers to determine their, what I'm gonna call difference. So you're comparing, okay, now, it's not an accident that the word you're looking to compare the differences. It's no accident because the subtraction model, A minus B, is called the difference equation. The difference simply means this subtraction. So our equation 8 minus 3, using the comparison model, we list both sets of numbers. And we see how they're different. They both have 1, 2, 3. This is where they're different. How many numbers are there? 1, 2, 3, 4, 5. So 8 minus 3, the difference is 5. Okay, now we'll look at the subtraction properties. We have two more parts. We have properties and algorithms. Algorithms are step-by-step instructions. Okay, let's look at the properties. Whole number subtraction properties. So to find the difference between any two whole numbers, so excuse me. Find the difference between any two whole numbers, eight minus 3. Eight minus 3 exists if and only if. Okay, now whenever I use if and only if, I'm simply going to write IFF. 8 minus 3 equals some number C exists. 8 minus 3 equals, I need to tell you what it equals. If and only if 3 plus that number C is equal to 8. Right, so. And C is a whole number. Let's look at this one. Is there a number C that will satisfy this equation?
For the negative.
Right. This one, since 5 is bigger, that means C has to be -2. Because 5 plus C has to equal 3. Since C is not a whole number, this does not work. If it doesn't work, you said it is not meaningful. Basically, it's this. What is this? This is summed up. It says this. For A minus B, if A is less than B, A equals C. Then C is not meaningful. In the set of whole numbers. Which means it's not closed. See, all these things fit together. If it's not meaningful, that means it's not in the set of whole numbers. If it's not in the whole set of numbers, then it's not closed. So it's not closed if A is less than B of A minus B. So your general statement, remember we're still talking about the properties. So the set of whole numbers is not closed under subtraction.
So what is it like? A decimal, so let's say like 1 in 5, like 1.5. Will that still be like considered not close or considered close?
It's not a whole number. Whole numbers are numbers, no decimals. But yeah, once we go to different, if we introduce decimals, then we introduce the real numbers, and that's positive, negatives, and zeros. Good question, though. Yeah, it's just that that's why you have to define what number system you're using. And for elementary school kids, we first start off with the counting numbers, then we introduce zero. Because anytime you hear a teacher count in elementary school, it's always 1, 2, 3, 4, 5. Never 0, 1, 2, 3, 5. So we start off with the counting numbers, then add the zero, and then put the negatives in eventually. Once it's algorithms. What's that?
Why we never start counting from 0?
Zero was, it took a long time for zero to get invented. None of the systems, the early number systems, ever used zero as the first number. They used zero after like the 1, so you have 10, hundreds, thousands, but they never had zero as a number by itself, because how do you define nothing? Remember, it all started with commerce, trade. If you're trading 3 sheep and 4, I'm going to trade nothing for your cow. So again, it's just a concept that wasn't really needed until you get to subtraction, which it showed that everything's perfect. Because if you had 4 cows and I had 4 cows and we traded them, so, or I gave them all to you, so I have no cows, you have 8 cows. So it's a concept that wasn't really thought of until hundreds of years later. Algorithms of subtraction. And we pretty much discussed the first one already. It's the base 10 blocks. If you remember, we had the 31 minus 16 or 15. So using the blocks, if you can't take 5 away from 1, then you have to borrow the next bigger one. So that means now there are 10 more. Now we can subtract 5 and 5, leaving us with 6. Then 2 minus 1 is 1. The equal addition algorithm. We've talked about that. To equal, what do you think the equal addition algorithm is all about? Taking the numbers you have and changing both of them the same amount to make them easier. For example, let's look at 37 minus 15. So let's look at the bottom number, the smaller number. If we take the bottom number and add 5 to it, what do we get? If you add 5 to the bottom number, 20.
I'll think of like what it count for the negative.
No, but this is not a negative, it's a subtraction. Since we added 5 here, we add 5 here. So 37 plus 5 is 42. Now it's a lot easier. So what you're trying to do is get the bottom number to be a zero number. So now 2 minus 0 is 2, 4 minus 2 is 2, so 22. It also works with bigger numbers. 255 minus 163. Let's look at these. Just see how far we have to go. Again, look at the bottom number. The first thing we can do is try to get it to be 70. So we add what? Add 7. So add 7 top and bottom. That gives us 170. 255 plus 7 is 262. Okay, so that got rid of the first digit. Now we have to get rid of the second digit. So we add 30. Well, I'll show you why. 170 plus 30 is 200. 262 plus 30 is 292. So now, once we have all these zeros here, it's a lot easier to subtract. 292 minus 200 is, I mean, all you have to do here is pretty much add. And at the very end, since you have zeros on the bottom, let's look at another one. 413 minus 247.
The first one would be 3.
All right, so we add 3 to both of them. Which would bring the bottom up to 250. And 416 on the top. Then
50.
So 250 plus 50 is 300. And then 416 plus 50 is 466. So it's 6. 4 minus 3 is 1. So the difference is 166. It's a little bit of front end work, but it's at the end, it's much easier to deal with. A lot of people are very comfortable with addition. It's if you try to do this one or even this one, it's a lot of moving numbers. Borrow 1, move this over, but this way it always works. Get them all zeroed, and there you have it.
So I have a question. So are the answers all the same, or they change because you're adding?
You're adding the numbers you add is always going to be different depending on the bottom number.
I'm talking about like, so okay, so 413 minus 247, does the answer so equal 166?
Let's see. Okay, 3 minus 7, you can't do it, so you got to borrow 1. 13 minus 7, 6.
Then you have to borrow another one.
You borrow 1. 10 minus 4,
6.
3 minus 2.
Okay, that's no, I think I was wondering, do the answer,
Yes, it will, because since we changed the top and bottom numbers the same amount, the difference is still going to be the same, no matter what. So again, that's one of the easier methods of doing it.
That's the thing that I was curious about.
Yeah, it's a good question. Okay. And what number was that one? That was number 2. Number 3. Is the count up algorithm. The count up algorithm. This is also known as the making change algorithm. You've seen this 1,000 times already. You go to a store and buy, let's say, $13 worth of merchandise. And pay with a $50 bill. How much change will you get back? Remember, you're at a store, so this is what you normally see. They first check to make sure it's not counterfeit. Then the first thing you do, they start at $13. Then they give you $1 to make it 14. Then give you $1 more to make it 15. From 15, they give you a $5 bill to make it a 20. Remember, you have to get up to 50. So then from 20, you go up to 30. I give you a $10 bill. And then from 30, I give you a $20 bill to make it 50. You see it all the time. 13, 14, 15, 5 is 20, 10, 30, and 50. That's how they do it. So the total change that you'll get is if you add up all these bills. 20 plus 10 is 30, 5, 37. $37 change. And that's the reason it's called a count up or the make change, because you start with the number you ended up with and add up from there until you get, once you get 15, then you go 5, then you go 10, then you go 20. The same scenario. $13 bill. pay with $100 bill, what kind of change will you get back? So, this is zero. So you get $1, that puts you up at 14. You go up another dollar, makes you 15. Then go up $5, jumps up to 20. Remember, we're trying to get to 100. So from 20, they give you a $20 bill. That goes 40. Then another 20. So how many does that give us? 20, 40, 60, 80, 5, 6, 7. And that's what they use at cash registers all the time. And the last algorithm is called the trade first algorithm. In this method, all columns are regrouped. Before subtraction. Before subtracting. Because let's say we had 122 minus 17. Or make it 37. I want these to be bigger. Traditionally, how would you do it?
You first you borrow.
Borrow one from there.
Borrow.
Then we got borrow one from there again. So you do it as you go along. What the trade first does is I need to get these numbers bigger than the bottom numbers. So those get changed first. 11. So I borrow my 1 from there. The 10 from there makes it a 12. Borrow the 10 from here, make it 11. Now I subtract. 12 minus 7 is 5. 11 minus 3 is 8. So you take care of all that moving around first. So far, so good. Subtraction with numbers in other base systems. base 5. Were you here? Were you here when we talk about the base system? Okay. Our number system is a base 10 system. Which is why they're called decimal places. Deci is 10. Now, what are the numbers that comprise? Here's where it gets now. You asked earlier, why don't we ever start teaching from 0? Let's see why it's a base 10. So start at 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. What comes after 9? Yeah, so that's the first row. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And then the next one jumps up again. So it's 21, 22, 23, 24, 25, 26, 27, 28, 20. So the last digits will always be 0 to 9. There is nothing else that could be there. Once you reach 9, you're done with the last digits. Now it jumps over to the next column, which is the tens. And how many numbers are there from 0 to 9?
10.
Yep. Hence base 10. So basically we're going to see here that since it's a base 10, the largest number we have is 1 less than it. The number 243. There's 2 of these, there's 4 of those, and there's 3 of those. These are the ones. These are the tens. These are the hundreds, right? This is how we determine what they are in each column. Since it's a base 10, this is 10 to the 0, 10 to the first, 10 to the second. Anything to the 0 power is 1. So this is 1 times 3, makes it a 3. 10 to the first is 10. 10 times 4 is 40. 10 squared is 100. 100 times 2 is 200. If you add up all these 3, you get 243. That's where the numbers come from. Our addition. Remember these numbers. This is the tens column. That's the one. So it's 2 times 10 to the first plus 9 times 1. Next number, the 10 here, the one here is 1 times 10 to the first, 5 times 1. When we add, we have 2 times it, so we have 2 plus 1 times 10 to the first plus 9 plus 5 . So this is 3 times 10 to the first, 14 times 1. Three times 10 is 30. 14 times 1 is 14. Add these numbers, I get 44. That's what happens mathematically. But what we've done here is 9 plus 5 is 14, carry the 1. This is what happens in number systems. So let's look at a base 5 number system. Right. Let's look at a base 5 number system. So in a base 5 system, what numbers can we use?
0, 1 through 4.
Right. It's always one less than the base system. Because you can't 0. So each digit in a base 5 system the first digit is based on 5 to the 0 power. 5 to the first, 5 to the second, 5 to the third, 5 to the fourth. Because it's all base 5. So if I gave you the number 23 base 5, I'll write it out. If I give you this number, you don't read this as 23. Because 23 is a base 10 number. This is read as 23 base 5. So what would that be in our number system?
Now, or you talking about
In our base 10?
it will be 2 times base 1. I mean 10 to 1, 10 over the 1 power.
No, we first convert it. The second digit is 5 to the first, so it's 5. 5 times 2 is 10. This is the ones. 3 times 1 is 3. So 10 plus 3 is 13. This number is the same as 13 base 10. As we take these digits and put it under the appropriate column, this is how we convert it from base 5 to base 10. (32 base 5 minus 14 base 5). We can use blocks, base 5 blocks here. This first column, it's made up of singles. This one is made up, the bar is made up of five up and down. This other one is made up of 1, 2, 3, 4. 1, 2, 3, 4. It's made up of 5 columns of these 5 bars, and so forth. So what do we have here? We have 3 bars of 5. 1, 2, 3, 4. 2, 3, 4. I'm sorry. So that's the 3 base 5. I have 3 bars and 2 singles. What would go to the next one?
1 bar and 4 singles.
And then 4 singles. Very good. Can I subtract the singles? No, so what I gotta do?
Square bar.
I gotta borrow, so I have 5 more now. So I gotta take 4 away. 1, 2, 3, 4. Leaving me with how many ones left?
Great.
Mhm. Now, how about the bars?
It will be with 1.
So the answer is what? I can't say
I
13.
mean, oh, sorry. Like 8.
It's 1, 3, base 5. Yeah, that's the hardest part because 1, 3, that's 13. No, the 13 is a base 10 number. So this is how you do it in base systems other than that. All right. And that's the section. Oh, God, yes. I mean, when we do subtraction, 7 minus 5. No, there's a whole bunch of ways. We have to introduce it to the students somehow that they'll understand it. Okay, so that's it for today.